Linear algebra. Algebra that has to do with lines. Okay? So there's lots of applications to linear algebra, engineering, physics, a bunch of other stuff, computer science. What we're going to start off with is something you have done before, and that is solving linear equations. So a linear equation is like y equals mx plus b. That's an equation of a line in 2 dimensions. We're also going to look at some lines in 3 dimensions and think about what does it look like if you had a line in 3 dimensions and you had to solve that system of linear equations. You could have lines in 4 dimensions, 5 dimensions, 6 dimensions, although you can't quite imagine them, but we will be able to solve those systems of linear equations. This unit, one of the things is looking at different techniques for doing this that you started way back in grade 10. So here, a system of linear equation is a set of m linear equations. So far, coming up till now in grade 10 and 11, you might have done 2 equations with 2 unknowns. Did you do 3 equations with 3 unknowns? Maybe a little bit, maybe once, and then it got scary and you went away. So now we can do m equations of n unknowns. Now, when you just have a line, before we do this one of the things that sometimes a teacher does in grade 10 is they have a line and they say solve. Yeah, for what? You can't solve for x. Can you tell me what x is? Well, x can be a bunch of different things, right? Because it depends on y. And y can be a bunch of different things because it depends on x. And there's not just one solution to this, because the answer is the whole line, which has a bunch of different points. And every single point on the line is a solution to this. So when x is 1 and y is 8, that works out to be one of those solutions. But once you have 2 lines, and there is supposed to be here, I don't know if it's corrected on yours, an equal sign here. Oh, there's an equal sign after the 1, so that means maybe it was supposed to. Does yours have equals 0? Okay. Good, I fixed it on yours, didn't fix it on mine. So we have 2 equations of 2 lines. What could happen is quite likely those 2 lines, will intersect at a point. So you learned techniques for solving this. You learned 2 techniques for solving these systems of equations. One technique was called substitution, and one technique was called elimination. So we'll solve this one using both of those techniques to remind you of what they are. So I'll split the page here in half. If you want to use the technique of substitution, then you had to get one of the variables by itself. Usually you looked at both equations and you decided, what's the easiest to get by itself? Is it easy to get x equals or y equals? Sometimes they're both equally easy, but in this one, I think one is easier than the other. Can you see that it's probably easiest to get x equals? All you would have to do is to take equation, I'll number these. I'm going to call this equation 1 and this equation 2. You take equation 1 and you move the 4y over to the other side by subtracting, and you get x by itself. Once you have x by itself, you want to substitute what x is equal to, negative 4y plus 6, into the other equation. If you plug it back into the same equation, you're not going to get anywhere other than do a bunch of math to find out that either 0 is equal to 0 or 5 is equal to 5, or you can find other fun facts like 3 is equal to 3. But it doesn't help you solve because everything will cancel out. So it's important to know that when we got x by itself, this was still equation 1. And when you substitute in, you have to substitute that into the other equation. And the other equation was 2x, but now instead of x, we substitute the fact that x is equal to negative 4y plus 6 minus 3y plus 1 equals 0. So we substitute it into equation 2. Once you've done that, now is just the algebra part of putting your like terms together. Wait a minute. All right, did I make a mental math error? Okay. Where did I make my mental math error? You got 13 over 11? It just felt right. You get this feeling like, shouldn't it be a nice number? Because you're so used to it. No, I guess it's not a nice number. Now I'm getting, my job this year is to get you used to horrible numbers. Okay, excellent. This is a wonderful example. I love 13/11ths. Right? Make such a nice decimal. 1.18 repeated. Yeah. Okay. All right. So 13 over 11 is y. Now that you've got y, you can plug that back into either equation. I would probably choose plugging it back into equation 1 to find out x. Now x said it's equal to negative 4y plus 6. Solving for this, we're going to get negative 52 over 11, get a common denominator, plus 66 over 11, and x is equal to 14 over 11. Also another nice number. That's 1.27 repeated. Yes? Ooh, good. I'll show you that. Okay? But we'll solve this first in both techniques, and then we can get off topic, because that's a topic I like to get off topic on often. Good. Whew. That was close. All right. Elimination. With the elimination technique, what you want to do is you want to line up your equations so that you have one column that's all of your x's, one column that's all of your y's, one column that's all of your numbers. It doesn't matter how you do that. Usually, like in this case, I've got my x's and my y's on my left-hand side of the equal sign, but my numbers, one of them's on the right, one of them's on the left. So I'm going to just, first of all, take my equations, and I'm going to say, I'm going to organize them this way. So everything lines up in columns. Now, the object of elimination is to eliminate a variable. And you do that by taking your equations, and I like to get the same number in front, but one positive, one negative. So I'm going to either look at my x values or my y values and decide which is easier. If I have to multiply an equation by a number, and sometimes you'll have to multiply both equations by a number, but which variable is going to be the easiest to eliminate? And in this case, it's going to be the x. Because if I take equation 1 and I multiply everything in equation 1 by negative 2, can you see the coefficient in front of x? I'll rewrite equation 1 and equation 2. The coefficient in front of x is now going to be exactly the same as the second equation, except one of them is positive and one of them is negative. Negative 2 and positive 2. Because now I can take equation 1 and equation 2 and add them together. And when I add my equations, so I add my columns, all my x's go away. And I'm left with negative 11y equals negative 13. Divide both sides by negative 11, and we get 13 over 11 for y. the same thing we found with our substitution method. Then once you get 13 over 11, dot, 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 you can get 14 over 11 as well. Same way that you just substitute that 1311 into equation 1 or into equation 2. Both are good techniques. Sometimes you're going to find the elimination technique, something lines up really nice at the beginning, you want to use that. Sometimes substitution just seems to be the best one. I like you to be able to work well with both of them to make that decision, because I do feel that there are times that one technique works way better than another, and so they're both very useful techniques. So the question was, mental math-wise, how did I figure out that this was 1.18 repeated? First of all, I don't know when I started learning my decimals, but I felt it was a useful skill to have. Like, how many fractions do you know to change to decimal? Do you know half? Yeah, 0.5. So when do you stop? Do you know a third? 0.3. Do you know a quarter? So it's probably, a lot of people get stuck at 1/6, right? A lot of people, if they get 1/6, they get stuck at 1/7. 1/6 is not so bad because it's half of 0.3 repeated. So you can get 0.16 repeated. 0.7 is probably the first hardest one, but very cool one. 0.142857 repeated.
That's where I stopped.
Yeah, okay, that one is, usually people skip 1/7 for that reason, right? It's easy to remember. If you can remember the 1/4, just double 1/4 and you get 14, you get 28. Double 28, make a little mistake, you'll get 57. So it's not too bad for memorizing. But I'll show you fun stuff with 1/7 in the end. So eventually you get to things like 1/11. And 1/11 isn't really, I mean, it's 0.09 repeated. But how do you remember 1/11? It's easier if you know something about nines. Do you know what 1/9 is repeated? Do you know what anything over 9 is repeated? As long as that's less, like actually a fraction. We're not going to do 2,000 over 9. Like point n repeated, right? 1/9 is 0.1 repeated. 2/9, 0.2 repeated. 3/9, same as 1/3, 0.3 repeated. The same thing happens nicely with 99, 999, 9,999, 99,999, and so on. Is if you have something over 99, pick a number, your favorite number less than 99. 72. 72 over 99 will be 0.72 repeated. Pick something fun over 999. Some number that you feel has been misrepresented. 637. That will equal 0.637 repeated. So if you know this fact about 99s, all I did was once I had 1 and 2/11ths, I said 1 and 2/11ths is the same as 1 and 18 over 99, and I got the 0.18 repeated. So that was the math thing that I did there to get that decimal place. So knowing something about the 99s and then working with that. Have I showed you fun stuff with 1/7? So pick another number over 7 other than 1. Something, sure. Or we could do 10. So 10 would be 1 and 3/7, right? And that will be 1 point. Now, if you look through this repeating decimals, can you see that this is 1 is the smallest number, this is the second, 4 is the third, fifth, fourth one, fifth one, sixth one, right? So if you want 3/7, you're going to have to start with the third number. It's going to be 4, 2, 8, 5, 7, 1 repeated. What? What? Yes. Pretty cool. So 5/7 will equal decimal 7142285 repeated. And you can do all of your sevenths. That way they'll have that pattern stay forever, which is pretty cool. Anyways, we aren't interested in cool math. We want to solve systems of equations. So when we solve our equations, we're looking for the point of intersection. And often, if we go back to the one we just solved, we will write our solution that way. We will write our solution as a point. The x-coordinate is 14/11. The y-coordinate was 13/11. Great numbers. And that is the point where they intersect. And when you have two linear equations, we have three types of solutions. You could have a solution that is independent. That's one answer. That's when those lines intersect. That would be two lines with different slopes. Okay? They wouldn't have to have, here, let's take this out. The only thing that's important here is that they have different slopes. Any two lines with different slopes will intersect. You could have something that's called a dependent system. Sometimes the same line gets written in different ways. I mean, this and this are the same thing. I just moved the 5 over. But if they said, ooh, here are two lines, when do they intersect? You'd be like, they're the same line. However, sometimes it's not quite as easy to see that they're the same line. Like, I might write this equation as wow, why did I choose such big numbers? Right? You'd be like, whoo, I didn't recognize you. Yeah, I forgot the y. There we go. So what did I do? I just multiplied everything by 212. Why 212? I have no idea. I think it's because I first chose a number that was even worse. And for whatever reason, 212 came to my mind next. But I wanted to choose something that the numbers were big enough that, oh, I don't know my 212 times table. You wouldn't right away recognize, oh, 1060, that's 5 times 212. And so those equations don't look the same, even though they are. So if you have two equations that are the same line, the same slope, the same y-intercept, when you graph those, here's the green line, and then here's the black line. And they're the same line, and you say, how many times do those lines intersect? Well, they're exactly the same. They're always intersecting. So we have an infinite amount of solutions in this case. Of course, right now, we're only talking in 2 dimensions. Once we get to 3-dimensional lines, things can get a little different. And then you have an incompatible system. You might have 2 lines that have the same slope, but they have a different y-intercept. If that's the case, those 2 lines will never intersect. Unless you want to invent a new math where you need them to intersect, then you can do that and have them intersect at an infinity. But we won't go there. Okay? But there are some natural applications of that. For example, When you do physics and sun rays come in, sun rays always come in parallel lines. That would mean they never exist somewhere else together, but you have a sun somewhere far away. That's like a big point. I know, it's crazy. So maybe they're not quite I don't know. So we can solve these. We've already talked about elimination and substitution. Those are your two algebraic ways to solve them. You can also solve them by graphing. If you're graphing, and while you're graphing, things work out so nicely that they intersect at a point that's so obvious, then you can find that out. The first example that we did with the 13 over 11 and 14 over 11, graphing would not have been nice. Because you would have saw they intersect, but you would not have been able to tell because it didn't intersect at a nice lattice point on your graph paper. So solve this one. Let's see, I'm going to get you to solve these next couple, but instead of doing all the methods with all of them, let's do substitution technique for this one. So you guys used substitution, probably got x by itself, right? And you substituted in, and you got negative 4y plus 2 plus 4y equals 2. You combine like terms and you got the fact that 2 is equal to 2, and now you were like, uh-oh. I thought I was solving for y, and everything went away. Okay? What have I done in this question is that I set up something that is always true. 2 is equal to 2 is always true. Looking back at your equations, can you see that they're the same equation? I mean, if I took equation 1 and I multiplied everything by negative 2, I would get equation 2. So this is a dependent system. It has an infinite amount of solutions. Because they're the same lines. Any time that you, either through substitution or elimination, while you're solving, you get something that's always true. If you get something that's always true, then it's going to be a dependent system, which always works. Determine the value of k so that this has no solution. So what do we need for no solution? These have to be parallel lines with same slope, but a different y-intercept. So one thing you could do in these equations is, if you wrote them in this form, then you would know what the slope of each line is. So if I take equation 1 here, and I rearrange that, can you see that you'd get ky equals negative x plus 2, dividing by k, that's rewriting that equation in y equals mx plus b form. With equation 2, we could do the same thing. Equation 2 is a little bit easier. All you have to do is so first of all, we notice that we've got two different slope expressions here. For equation 1, the slope is negative 1 over k. For equation 2, the slope is negative k. If they're going to be no solution, we know that they have to be parallel. And if they're parallel, their slopes would be the same. So we would know that negative 1 over k would be the same as negative k. How do we solve this equation? Well, if you multiply both sides by negative k, you'll get 1 equals k squared. So k could be plus or minus 1. That would make the slopes the same. Yes?
You could say that k equals 0, and then we have x equals 2, and then that's just not possible.
Well, if k is equal to 0, then you've got x equals 2 and y equals 4. If you think about those two lines, one of them's a horizontal line, one of them is a vertical line.
But you're not allowed to have x equals 2.
Why can't x equal 2?
Because in line, you can't cross the line more than once, whatever that thing's called.
Well, it makes it a vertical line. X equals 2 is a vertical line.
But then at x, one's y. I mean, at x equals 2, what's y?
Anything you want. So k equals 0 would still be a possibility, because you could have the solution 2 and 4. Because we want to look at, I'm going to put a red box around the slope, and equation 2, that's my slope, and equation 1, that's my slope. And if those slopes are going to be the same, then negative k has to equal k. So we get k could be plus or minus 1. The second thing, we aren't quite done, because there is a possibility when you plug in this k that you might get an infinite solution, same slope and same y-intercept. But if we look at our y-intercepts, which I'm going to put a green square around, can you see if you plug in either positive 1 or negative 1, your y-intercepts are going to be different? Because when I plug in positive 1, this y-intercept is 2, negative 1, this y-intercept is negative 2. In equation 2, the y-intercept is always 4. So in solving this, determine the value, there should have been a bracket S here, of k that has no solution. The values are plus or negative 1. Here's one for you to solve. Let's say you play around with this one and use elimination. So I took equation 1 and I multiplied by 6 to get rid of the fractions. 6 is the lowest common multiple between 2 and 3. So that would leave me with 3, after the 6, 3 times x minus 1, or 3x minus 3. 2 times y plus 2, or 2y plus 4, equals 24. Rearranging like terms and stuff gave me 3x plus 2y equals 23. When I wrote that out and I wrote the equation underneath, which variable is easiest to eliminate? Well, the y's already match up nicely. So when I add the two equations together, I'm going to get 4x equals 28. And plugged in 7 for x, and I get y is equal to 1. So this is one way of doing this one. It works out really nice for the elimination because 2 of your variables are already the same. So work on this one with 3 equations and 3 unknowns. What you generally do with 3 equations and 3 unknowns, since you have 3 equations, you take 2 of them and eliminate a variable. So for example, can you see if you take equation 1 and equation 2, you could use elimination really quickly and get rid of the x's. Then you take 2 other equations. So you used 1 and 2, so now you have to either use 1 and 3 or 2 and 3 and eliminate x again. What that will leave you with is 2 new equations that just have y and z. And then you have 2 equations with 2 unknown questions to solve from there. The most typical thing that people see here is that your x and negative x are the same. So if you added those equation 1 and 2 together, you got rid of your x's. I'm labeling that equation A. Now, whether you used equation 1 and 3 or 2 and 3 next, okay, I took 2 and 3, I multiplied equation 2 by 2, and then added them together. And this is where you might see your mistakes. X's cancel out again. I get a new equation with y and z, or y and z. Now you take equation A and B, and I took equation B and multiplied it by a negative number. So my y's matched up, added them, got negative 2z equals 4. That allows me to find out what z is. I can plug in that value of z into equation A or B and find out what y is. And then I can plug in z and y back into the original equation and find out what x is. Solving for that, you get your solution. Again, we can write our solution as a point with x, y, and z in that order. Now, looking back at the 3 equations, some people might notice and say, hey, the z is already out of equation 2. So you could have used equation 1 and 3 and tried to cancel out the z. That would be a little bit harder because of the coefficients are 3 and 5. You would have to multiply equation 1 by a negative 5 and equation 3 by a positive 3. And the coefficients would be the same and you could cancel them out. And it will work out to be the same values. So for the weight question that I put up at the end, you might have noticed you could set up a system of 3 equations for this. Cat plus bunny is 10. Dog plus bunny is 20. Cat and dog is 24. And solve for each of them. However, these puzzles, often you can find shortcuts for them. Do you notice if you put all 3 of the scales that you know together, that would add up to 54? And what would be on the scale if you did all 3 of those together? 2 dogs, 2 cats, 2 rabbits. So if 2 dogs, 2 cats, and 2 rabbits is 54, then 1 dog, 1 cat, and 1 rabbit would be 27.